This morning we have two more awesome lectures. The first one given by Luigi Nardi. He was at the University of Pierre and Marie Curie, now Sorbonne University these days, was doing his PhD there, then moved to London to the Imperial College actually, was there a postdoc, then moved further away from Europe actually, although he was born in Italy if I'm correct, yes, right? And then he was at Stanford even. And then he was coming back actually now to Sweden, to Lund University, where he's now a professor, but still associated with Stanford, right? So he has somehow a mixed position there. We know each other, I believe, now for 4 years. I think we met for the first time at ICML in Stockholm in 2018. Right. And working for several years already on a lot of stuff related to Bayesian optimization, automated machine learning. And I'm happy that he agreed to be here today and present our new stuff and maybe even more on user priors, actually. I think a very important field, and it's all yours.
Thank you. Thank you, Marius, for the kind introduction. Right, so 4 years ago, it's already quite a little while. Right, so, well, nice to meet you all. That's much better to be in person. I hope that we will enjoy this more interactive way today. So let's make this really interactive and ask questions as they arise instead of waiting until the end. You can find the presentation here, this link here. So I recommend that you have it on your laptop if you want to take notes. And okay, so today we will be talking about user priors for hyperparameter optimization. This is a topic that was mentioned a few times in other lectures. And we will also touch upon the Bayesian optimization topic that was mentioned many times, but we didn't really take the time so far to go a little deeper and try to understand what that really is about. So about me, Marius introduced me already. So I have I'm an assistant professor at Lund University, part-time at Stanford at this point, and my main focus is on Bayesian optimization and a number of interesting applications. The interesting thing with Bayesian optimization is that you can use it across a spectrum of different applications. And here today, I will show a couple of examples in automated machine learning, hardware design, and robotics. So we'll briefly touch upon those applications during the talk, and perhaps towards the end. So feel free to add me to your favorite social network. I'm pretty active on Twitter and LinkedIn, not so much on TikTok, unfortunately, but maybe one day. So yes, so very briefly, the research team, you can see Marius and Frank here. This is the research team that is related to this specific topic. We collaborated with a number of people over the last perhaps 4 or 5 years, and the main leads are Arthur here. Okay. And Carl. So they're not here today, unfortunately. You may have seen Leonard during yesterday. I don't know if it's here today. Anyway, so the outline, we will give an introduction on this topic on human-centric hyperparameter optimization. Give a brief introduction of Bayesian optimization. We'll try to give a slightly deeper introduction than what was given before. And my hope is that by the end of this lecture, you will be able to understand the keywords in Bayesian optimization. And then at the end of this lecture, go and download your favorite library, and you will know what the wiki pages mean. Like all the keywords you will know, right? And then you will be able to use the library right away. So that's the goal for today. Then we will talk about user priors, specifically in Bayesian optimization. And we will talk about the application to hyperparameter optimization first, and then I will give you a couple of exotic applications that I find very amusing, very interesting. Give some conclusions and future work after that. So let's get started. And as I said before, let's keep this interactive. So you can ask questions whenever you want, and I will feel successful today if I will receive the first question before slide number 10 or something like that, okay? Right, so this is the machine learning meta challenge. So this is machine learning has been getting more and more complex over time. So we saw many talks on this topic. So there are many parameters that affect the performance of machine learning models in a broad sense. So we've seen this in deep neural networks. You know, a well-tuned neural network can lead to much better performance. And specifically here, I mentioned the type of parameters that the type of hyperparameters that you can tune with this hyperparameter optimization techniques, right? So the number of layers, regularization, nonlinearities, batch size, learning rates, and so on, right? This is not just about deep learning. So if you look at other models, for example, random forest, you also have a number of parameters, right? So the number of trees, you know, the max features, the criterion, and so on. So this trend of having hyperparameters that will heavily affect the performance of your model, it's a common one across the board, right? What we do usually is to define an objective function, which in the context of hyperparameter optimization is generalization performance, cross-validation, and so on. I think you guys know these kind of things pretty well. And then yesterday, Kata, or maybe 2 days ago, Kata was talking about the different methods that you can use, and very common ones are grid search, defining some sort of grid on your hyperparameter search space and doing that automatic sweep of the hyperparameters. Then we briefly mentioned in the last couple of days random search, which works surprisingly well, and I think it's always good to have it in our research papers to show how we compare against that. And then there is this, they call it dark magic. For me, it's really dark magic, right? So there is a ninja developer, very well aware of the application in hand, and this person is able to, you know, smell the parameters, right? So this should be this value or that value, right? And usually these people are very rare. They are, you know, difficult to find, and you know, the objective of hyperparameter optimization in an automated fashion is to try to reduce the need of this type of expertise, right? So this hyperparameter optimization is usually painful. The training can be, yeah. Yes, thank you for the question. So the question was, can I give an example of a ninja developer? A name. Andrei Karpati. I think he is. Yeah. So Andrei Karpati, I think he's not Tesla anymore now, but he was one of the creator of the deep learning course at Stanford. Then joined, I think, a startup briefly, then went to Tesla to direct their AI operations, and was working on computer vision for autonomous driving. And he's a person that he went all the way down to programming neural networks through weights by writing the weights himself without training. So I would say that he's a ninja developer for that type of application. Of course, there are other applications as well, and in hyperparameter optimization, that would be a ninja developer. But in the broader context of Bayesian optimization, if you have a person that has 20 years of experience optimizing a specific application, that I would call him or her a ninja developer. So this is not a name that I invented, by the way. People use this a little bit out there. So anyway, thank you for the question. So been very successful because it's slide number 9. So this is very expensive in terms of time or money, usually, and energy consumption as well has been a concern in the past, and perhaps still in the present. You need many training cycles. This process is possibly noisy as well. So one of the alternatives to this HPO problem is Bayesian optimization, and this talk will mainly talk about this today. So briefly about Bayesian optimization, the field is not super new, but recently we saw a number of success stories, including the, AlphaGo. AlphaGo, it's, nobody talks about Bayesian optimization with AlphaGo, they talk about other things, but because the Nature paper roughly mentions that, but there is another paper that talks about how they tuned the AlphaGo system, and it's purely based on Bayesian optimization. So this is an archive paper. I don't think it was even published, but you can read it. It's quite interesting, right? So there is the flashy stuff on the Nature publication, and then there is how we actually made it work, right? And there was a double-digit performance improvement using Bayesian optimization. We talk about double-digit performance improvement, so non-negligible. Other success stories, we saw this in Frank's book on automated machine learning. There are a couple of companies out there now, Google, Facebook, and Amazon and so on. They are releasing tools that are based on Bayesian optimization, can be used, and this is really speeding up the field and the applications as well. So talking about Botorch and Google Bezier that was also released recently. Bunch of different applications here. I will be talking briefly about this application here on hardware design, and then other applications. You can find tens and tens of applications of this kind of things. However, BIO is effective and the experts use it, but the larger audience doesn't use it very much. And there was this review by Bottier and Varaco in 2020, where they've been asking people attending NeurIPS and SCLR what were their favorite methods for tuning hyperparameters, and this was the answer. So it doesn't look very good. Most of them it's manual tuning, half of them perhaps. Then there is a big chunk which is grid search. There is a bit of random search, and then there is other. And other doesn't really need to be Bayesian optimization. It can be Bayesian optimization, it can be also something else. So this is somewhat worrisome because the tools are ready to be used, but the community is not responding to this input, right? And so what's the reason, right? Perhaps there are multiple reasons. So Bayesian optimization can waste some evaluations on poor designs because we will go in detail, but Bayesian optimization learns a model, a surrogate model that exploits to drive the optimization. And so to build that model, there is a little bit of observations to be gathered before being able to really exploit this model. And it disregards user beliefs, meaning that if you are a Ninja developer, if you're Andre, and you want to do hyperparameter optimization, then you will probably not trust this tool because you have 10 plus, maybe 20 years of experience doing this yourself, and you trust your own beliefs, right? And here, when I say beliefs, these are beliefs with respect to the location of the optimum, right? Where does the optimum? I will give an example on that. So the question that we ask in this talk is, can we incorporate expert knowledge in Bayesian optimization, right? So originally in 2017, I gave a talk at Intel Corporation in the Bay, and I was talking about this stuff. And at the end of the talk, they told me, this is great. We don't do any of this, but that would be great to do that. But in practice, we will never do this because you're blindly searching the space. So we are the experts. Why cannot we inject this expertise in the optimization, right? So, and I took that very seriously. So I went back to the lab, and the day after I was trying to write down how we can inject priors in the optimization, right? And the result was a few interesting papers that came out from that in collaboration with Frank and Marius. So the idea here is that practitioners usually have this two ways of doing, right? So the Bayesian optimization way or the expert manual tuning way. So you do this by hand or you use an optimization framework. As I was saying, the right one is the favorite method today. But the idea of this talk is, can we do this, right? So can we use this expertise to in the optimization process so that we speed up the optimization, so we can reduce the amount of time, the amount of resources, the cost that it takes to perform this hyperparameter optimization task. And one example that comes up from time to time, so if you have to define the best learning rate of the Adams optimizer, you can define a range and do grid search. People often say that it should be around 10 to the minus 3, right? Or somewhere around there. And perhaps you want to use that knowledge in this optimization, right? So this is the type of things that we would like to be able to use. Any questions so far? Yeah.
Why do you typically choose Bayesian optimization to combine with the beliefs and not something else?
That's a good point. So it can be done with other techniques as well. And Neratoy here in, I don't know if I see him right now, but Neratoy has been working with a method that is based on more random sampling and hyperband. So that can be done. I think it's so the beauty of Bayesian optimization is that you can integrate these things in a fairly sound way and create some posterior that can be exploited that way. But that's an excellent question. It doesn't have to be Bayesian optimization. Good. Okay, so let's talk about Bayesian optimization a little more in detail. So what we want to do here is to find the global optimum of an objective function. So the objective function can, for example, be the cross-validation error of a DNN, right? And this is expensive because it takes time to train, and it's expensive in terms of how much resources you have to use to train that as well. Then we build a probabilistic surrogate model. So this is a model, it's a machine learning model. It's probabilistic because it gives you the mean and it also gives you the uncertainty around the mean, right? So that's the way we call it probabilistic surrogate model. And the way we build this surrogate model is based on past experiments as training data, and we will go more in detail with respect to that. So the model that we build is much cheaper to evaluate with respect to the objective function. And so we can query it as much as we want, and it's cheap to optimize, right? So because you can easily optimize something that's cheap to query. And I will describe this loop a little bit more in detail in the next slide. But for now, the idea is that we want to globally optimize a function that can represent the cross-validation error of a DNN, and we build a model, a surrogate model, that mimics what this expensive function does, and then we focus on the optimization of this surrogate model. So common surrogate models are Gaussian processes for some reasons that we will describe, but there are also other models that, for example, SMAC and Hypermapper are based on random forest, but both implement also Gaussian processes. There's 3 Parson estimators, Bayesian neural network. So anything that gives you a mean prediction and error bars, right? So anything that gives you that can be used for this purpose. So going a little bit more in detail, the problem we are trying to solve here is to find the global minimum of this objective function G. So X is your search space. The search space in hyperparameter optimization will be, for example, the learning rate. So if you're searching learning rate, X represents, the interval you're searching. And you're trying to optimize G of X. So you're finding the minimum of G of X. But in practice, you're also looking into the argument of the G of X. So you're interested in finding the X that minimizes the objective function. So we can evaluate the objective function G pointwise, meaning that if I give you an X, you can give me a G of X, but there is a cost associated to that. The other constraint is that we usually don't know very much more about G. We don't have gradients, for example, usually, right? So we can query G of X a few times, but we cannot. We don't have analytical forms of G, for example. And observations can be noisy, and the evaluation is costly, as I was mentioning before. The training of a deep network, for example. So this is what you see, right? So these are 4 observations, so the parameter x on the x-axis, and then you have the objective g of x in the y-axis, and this is usually what you see, so just a few points, and what you're trying to do is to have the minimum amount of observations to optimize your function. Okay, so here I'm just really re-summarizing this again. So we are, so we want to avoid evaluating G an excessive number of times. That's why we build this surrogate model. And the surrogate model, which is usually a Gaussian process, it's cheap to evaluate. So we try to find a global optimum of this surrogate model. And what happens in practice is that the surrogate model, since we observed only a few points in the search space, will not be very accurate. And this method, of course, will work better if the surrogate model is accurate with respect to the objective function. And so this is usually not the case, at least at the beginning. But what we do is that we iterate, right? So we keep observing more over time so that we refine the model over time. So this is, an illustration of this process. So we have, and by the way, this is X here. Right. So we have the X from -5 to 5, and then on the black line is the mean prediction of the Gaussian process, and the gray band is the uncertainty around that prediction. And then there is the true objective, which is in blue here. So you can see that by just observing this one data point here, the Gaussian process can do, can model decently well around that point, but doesn't know very much on farther regions of the search space, right? And the idea here is to be able to match the black with the blue over time, but the point is not really to match it everywhere. We're just interested in finding the optimum. So this is not really just a full regression problem. It's a regression problem that is a driver for the optimization, right? So what happens in practice is that we see, for example, that there is high uncertainty here on the boundary, and perhaps it's good to explore there to know a little better what's going on in that region of the space. So we do that. Once that we observe that, we can refine our Gaussian process in that region. Then the next step is to check again. You see here there is a fairly a decent mean value there, like fairly low, but there is also a very big band. So that's potentially a good candidate for exploration again. And so we explored that, and slowly we are getting to the point where we understand better the black box function that we are modeling, and we're also getting a better hold of the optimum, right? So this seems to be a good point to explore again. And now we start to see that the minimum, which is here, it starts to be a little better represented by the model. We still observe that point over there, and then it becomes natural to start to optimize in this region here. And then we refine this over time until we get very close to the optimum, right? And here we basically found the optimum, right? So this is the general high-level view of what's going on. Of course, the search space is usually much bigger than just one parameter, but this idea of reducing the uncertainty, which is an exploration step, and the effect of exploiting what we know, which is an exploitation step, and combining these two steps together so that we can drive the optimization faster, closer to the optimum. Any questions on this?
The objective function may be noisy in itself, and is there a way for the Gaussian process to represent the noisiness of the objective function separately from the uncertainty, because we haven't explored the regions?
Excellent question. So the question was, can we model noise with Gaussian processes, right? The answer is yes. And this example, thank you for the question, by the way, this example is noiseless example, but I think I have some other examples where you will see that the observation here, for example, you see that it really matches the model and the black box function. They really match there because we assume there is no noise in this very specific example here. But in general, that doesn't have to be the case. Even if you observe there, the point may not be exactly on the black box function, which is a latent function. You don't really cannot really see it, right? So you will always see it with respect to a noise, random noise variable added to that, right? So yeah. So thank you for the question. Any other questions?
And is there some limit on the number of parameters that can be handled by the initialization?
So the question is there a limit on the number of parameters that we can optimize with Bayesian optimization? So this is an excellent question. So I think the current belief is that you can optimize a few tens of variables maximum, and usually things start to break when you go above 20 maybe. There are frameworks there are frameworks that deal with more variables, but that's a research topic. So high dimensional Bayesian optimization is a research topic, and it's a very compelling one. Leonard, my PhD student, just published a paper on NeurIPS where we are able to go all the way to 1,000 or even more variables. But that's on the research side of things for now. Right. So there are issues with the surrogate model that can break. For example, if you go to high dimensional, the optimization of the acquisition. I will go a little bit more in details of the algorithm afterwards. Maybe I will take that question at that point then. Yeah. Please, Bernd.
You allow me also to comment for 10 seconds on these questions about stochastic network optimization?
Sure.
I mean, I sometimes wonder a little bit why we sometimes have the impression that we under-discuss this a little bit. I mean, first of all, we do machine learning, right? So you said cross-validation. I mean, this is always stochastic, right? And so the assumption that it's noiseless is basically always wrong for us. We can use the GP as a regression model. I guess we are all doing that, I think, in all our implementations, at least a little bit, just for numerical stability. But you also, if you really look into this, using expected improvement is wrong. Because expected improvement is constructed under the assumption that the thing is noiseless, right? The objective function. But there are a lot of papers who have where special acquisition functions are also developed for the noise case. So basically, you have to use a regression model and you have to use a different acquisition function if you want to truly handle this from a mathematical or perspective. I don't know. I think we sometimes just use the noiseless version and then kind of keep our fingers crossed and that it works, and it sometimes does. I guess it also depends a bit on how big your test data is and how much cross-validation you do. But I guess in order to be fully correct, also from a scientific perspective, these shortcomings should be made. But this is all possible. It's just less used, but less explored. I think that it should be. Sorry.
Right. That's. I don't have anything to add on top of that. That's a good point. We will get into acquisition functions in a minute. This was just an example to explain. Of course, AI, which is this expected improvement acquisition function, which I will define in a minute, it's the mostly used one, and it's noiseless. Of course, there are versions of AI that is noise AI and AI as well, and that's a good way perhaps to mitigate at least that issue. And there are other acquisition functions that do that better, of course. Good. Any other questions? Yeah.
Are you going to discuss categorical parameters?
Not very much today, but the tools that I will briefly introduce, they handle them. Yeah. I will be happy to take a coffee with you and talk about that. Because we have a paper that will appear fairly soon on an application that has all the categorical and discrete variables, and we've been thinking quite a bit on how to do that properly. Good. Okay, so the idea here then was to so we have this idea of this is the mean and this is the uncertainty that we have, and we combine these two things together to find the global optimum. And global is important here to remember. So we're finding the global optimum. Right, so this is the steps of exploration and exploitation, and I will briefly define them here. So exploration means seeking places with high variance, and exploitation means seeking places with low mean. Right, so as simple as that. And the GP or Gaussian process, it's convenient because it gives us closed form solutions to calculating this mean function and the variance function as well. So that's pretty convenient, right? From a computational perspective. All right, so the acquisition function that Bernd just mentioned, I call it alpha here. And this is the function that specifically trades off the exploration and exploitation, right? So the way we combine these two things is guided by the acquisition function. So if you use one acquisition function, you will give more weight to exploration if you give or versus exploitation, and vice versa with other acquisition functions, right? So this is the hardest slide I have in this talk, and this is not really useful for this lecture here. This is how the inner workings of Gaussian processes look like, and if you're interested in this, I can share a presentation I gave in another summer school, in another school in the past, where I talk specifically about Gaussian processes. Happy to share that if you're interested. But here, what I wanted to briefly mention here is that Gaussian processes give you this closed form solutions to many of the useful questions that we ask. And the main actor for Gaussian processes is this thing called kernel. And a kernel briefly means just giving some sort of like similarity measure between 2 points in the search space, right? So if you have a point that you observed, and now you have another point that is close by, you will give it a higher weight in terms of correlation with respect to what you expect in this new point. But if you're very, very far from that point, then this kernel will tell you, I actually don't know very much of what's going on around here, because all the things I know about this black box function are far from where I am, right? So the kernel gives you this idea of distance in a formal way. And that's what we call K here, capital K. Right, and there are many kernels, and I think it's important to talk about this because this is also part of what will follow next, which is the priors that we can give to the hyperparameter optimization problem. By choosing one of those kernels, of course, you're kind of assuming that the function that you're optimizing looks more like perhaps this, or perhaps, you know, a little bit more like when you change direction, there is a little bit of more. So you're injecting this level of assumptions in your model, and that will reflect your optimization as well. So this, in some sense, is also an expert knowledge that we're giving to the optimization. Of course, it's very hard to use, right? So because if you're doing hyperparameter optimization, how would you know what's the best kernel to use? So this is something that is hard to use. All right, so where to evaluate next? So this is what the optimizer sees, and you can sample the Gaussian process. So this is what you get. So this again is a noiseless case. So if you sample the Gaussian process, you get a function, right? And now perhaps if you had to use this function to guess where the optimum is, you would probably, since you're minimizing, you would probably say, well, the optimum is somewhere around here. Right? Of course, this is a probabilistic model, and you can sample that again, and you will get something like this, right? So now it looks like the optimum is around here, right? But if you keep sampling, you will see that there are many of these functions that you can sample, like infinite. And what you want to do is to try to find some sort of expectation of where the optimum lies, right? And that will be, an information that is captured by the acquisition function, more specifically. And this is an example of acquisition function here. This is the one that Bernd mentioned before, so the expected improvement. And what this is really doing, this is an additional function that you have in your tool set. And it tells you, look, if you sample the Gaussian process, you get a lot of like this guys here that go all the way down here. So perhaps the minimum is somewhere around there. So maybe it's interesting to sample from that region to understand better what's going on. And so the acquisition function, this may be a little confusing. So we are minimizing the objective function, but we are maximizing the expected improvement. Okay, so here, if you maximize the expected improvement, you will see that there are these two guys here. So you probably will select the next point around here, which will, you know, sample somewhere around there. Okay, any questions on this? Good. How many are familiar with this topic already? Can you raise your hand? Oh, quite a bit. So maybe I'm being a little slow then, maybe. All right, so this is the formula for expected improvement. Here I will go a little faster then. So we saw this before. This is the Gaussian process in blue with the posterior uncertainty.
Some Microsoft Outlook directly in front of your equation.
That's
No, it's not.
it's gone. Great, thank you for. Right, so we saw this before. You're familiar with this, and this is the expected improvement. So here I'm showing iteration 6 of the Bayesian optimization process. So here we are, you know, 1, 2, 3, 4, 5. So we are iteration 6. We observed 5 times the black box function, and now we are going to iteration 6. We want to maximize the acquisition function. The maximization tells me that this is an interesting point to sample. So you do that, and then you do that again, right? So here now, the acquisition function tells you that this is an interesting point to sample, and you keep going that way. So we already saw that, and now we're going into the, you know, the pseudocode here, just to understand that this process is actually pretty simple, right? So you have a bunch of data that you can use at the beginning. You can sample the black box function a few times. That's your initial data set to inform the Gaussian process model. And then you go through a number of optimization steps where we update the GP given the data set that we already have. In this line here, we select the point just the way I was describing before with the expected improvement and acquisition function, for example, and we get the next x to evaluate, xn. Then we query the true objective, which basically means that we would be computing g of xn, right? And then we augment the data, and we keep doing this for a few times, right? In this for loop here. And at the end, what we do, it's there are possible options. One very simple option, it's just to return the minimum found in your data set, so in your D. Otherwise, you could also use the Gaussian process model to predict where the minimum is, and that may be a different approach, but both approaches may be reasonable. Right, so these are a number of acquisition functions that are usually used. I introduced the expected improvement. We'll not go very much in detail here, but these are perhaps the 3 most known. There is also Thomson sampling, and methods. Acquisition functions are based on information theoretical methods. You know, this is just for you to know that there are multiple acquisition functions. It's tricky for a person who doesn't know Bayesian optimization. Just choose one. The most used one, it's EI. And you can tell that it's the most used one because if you download a bunch of different frameworks, the default option is AI, right? There is research on this topic, and one of our NeurIPS paper this year was on information theoretical acquisition functions. And my hope is that in perhaps 5 years, we will have default information theoretical acquisition functions. So that's my hope. It's a more of an empirical observation. So there are also theoretical guarantees with EI, but there are also theoretical guarantees with LCB here or UCB. So those are useful to have. But I think that the community uses that for empirically based.
You mentioned theoretical guarantee for LCB.
Yeah, so I actually was going to just mention that right now. So in 2010, there was this paper, and this was awarded the 10-year test of time award by I think CML in 2020. So this was I think a good recognition for the field, and this paper introduces. I think it's written right here. So this type of regret bounds for GC, Gaussian process UCB, and this is for GP UCB, and there is another paper by Bull, Adam Bull, for the expected improvement as well, which is the noiseless scenario though. I had a slide that I removed because I thought I was going a little bit too in detail, where I actually talk about what these regret bounds look like. We can have that offline perhaps. So one of the tricky parts in Bayesian optimization is that we are creating this surrogate model, and now we have a similar problem, right? So now we have to optimize the acquisition function again globally, right? And this may be considered like a silly way to proceed, because we want to optimize a function, and now we are basically optimizing another function, but you're still optimizing globally that other function, which may be a tricky problem as well. So what have we gained, right? So the acquisition function is very cheap to compute with respect to the black box function, and so we can optimize it in a much better way, right? So you can use also gradient-based methods for that. For example, multi-start gradient descent type of methods, for example, for that. So it becomes convenient. All right, so let's go a little bit more in the more recent development with respect to this human-centric hyperparameter optimization with this idea of injecting user priors. This was the idea I mentioned before. Just to remember, what we said is that we want to use the Ninja developer expert in the Bayesian optimization loop, or in general in any optimizer, global optimizer loop. But here we will talk about Bayesian optimization mainly. So in general, you could say that this is not new, because we have been already injecting prior knowledge in Bayesian optimization before, right? So one simple way to inject prior knowledge is to take your search space and just shrink it. Instead of computing from -5 to 5, like in the example that I had before, you can compute from -4 to 4. That becomes like a prior knowledge that you're injecting. Of course, you have to know what you're doing, because you won't be able to recover from that, right? So once that you shrink the search space, then if your optimum lies outside that search space, then you will not be able to find it. You can bias the initial design. So for example, you can, in your library, you can have this default configuration, which will perhaps be your best guess, right? So these are all like expert knowledge type of prior injection mechanisms that have been around for a while. And you can, for example, transform your inputs and outputs. You can do log transformations, for example, so that you're warping the space in a way that makes more sense. You can do things like using a prior over function with GPs. So I was talking about the kernels before. So if you have an idea of what that black box function looks like, you can use a kernel that makes more sense for that function. Of course, this is very hard to do, right? That's why people don't do it, right? You can assume things like monotonicity, for example, of the objective. You can assume things like non-stationary covariance. These are hard things to do. You can use transfer learning, and I think that this topic was somewhat introduced before. So if you have a task that is somewhat similar, you can reuse the data, extract the knowledge from experience, and then be better at optimizing your new task, right? So these different methods are not really aligned with the knowledge that the user possess, right? Usually, users, what will be able to provide is something like, I roughly know that the optimum will be around this region. Perhaps I will put more emphasis in this part of the region and then less emphasis on the other parts, right? So, so knowing what ranges of hyperparameters tend to work well. And so that's why we would like to provide an interface that is very, very simple for the user to specify that. So for example, this is, I think, based on the Brannin 2D function here. And anyway, it doesn't really matter for this. But there is an optimum in Brannin that is around here. There's an optimum around here, and there's an optimum around there. And the user can potentially provide this type of insights to the optimizer, right? So put more emphasis here and put more emphasis here. So this is very simple to do. You can even use a tablet, right? And just draw this curve, which we will see, we will model as a density or a distribution, probability distribution, but in practice can just be a function that tells the optimizer to put more emphasis or less emphasis in some regions of the space. And it can be as simple as a univariate function. So here you see that I didn't do a two-dimensional density over the space. I'm just doing it in a univariate fashion. And anything that gives information to be exploited by the optimizer would potentially work here, right? So to go a little more specific here, this is again an example that we roughly saw before. Here we have the noisy observations I mentioned. This is the problem you're trying to solve. But now in input, you also have something that the user gives to you, which is this little bump here. So this is somewhat a Gaussian, truncated Gaussian perhaps, where the user is telling you that you want to optimize this function, so you want to find this minimum, but you also want to use this density. So now how do we combine these two things together? And the formula here is simply saying this, so the same thing that I just mentioned, but in a more formal way. So fx is the function that you are optimizing, and the user is giving this pi of x, which is a probability distribution over x, and this probability distribution is more peaked towards the belief of the user with respect to where the optimum lies, right? And that's said by this expression here. So this is the minimum of fx prime with respect to x prime on x. So that's the minimum, right? And you want to compute the probability of fx being equal to that minimum there. Any questions on this? Pretty straightforward, right? Very simple way. Everybody can use this. Takes a minute to define, and let's see if it works, right? So in practice, these are the type of distributions that you can easily define here. So you can, so if you have a named distribution, so a distribution you can name, you can input this by just writing the name, right? So Gaussian, beta, gamma, whatever. Otherwise, if you have a categorical or discrete set of parameters, you can define this in terms of a list of probabilities, for example. So very, very simple as well. Otherwise, if you have some points of observations that you already have, you can potentially compute a KDE, kernel density estimation, for example, and you will compute something like this. And that's also a density that you can potentially use, ready to use for this, right? So whatever your way of injecting this is, the interface is extremely simple and usable. So there are a number of desiderata for this method. The method I will introduce in a minute. So first of all, you want to be able to easily incorporate these expert beliefs, and I think I convinced you at this point that this is pretty simple if we use this distribution approach. We want to be robust with respect to the priors, meaning that sometimes the expert is just wrong. The application for some reason behaves differently, you don't know. You want to be robust to that. So you want to be able to recover from bad priors over time. And another interesting feature would be if you're able to have an approach that works across acquisition functions, that works across surrogate models, something that is fairly generic. easy to implement and things like that. Right, so here is the method. We call this PIBO. It's a prior weighted acquisition function. The approach then is to change the acquisition function somehow and augmenting the acquisition function with this expert prior under the form of a distribution, as mentioned before. And then we add a term that is dependent on the number of iterations in the Bayesian optimization. So this is given by n. This is the number of iterations, and beta is an hyperparameter of the method. So this is how it looks like. So we have the same expression as before here on the left-hand side. We just changed this with this little pi in subscript, which means that we also input this distribution at this point. And we simply multiply the acquisition function, whatever the acquisition function is, so EI or GPU-CB, etc. We multiply it with this prior, and the prior is weighted by this parameters beta divided by n, so that over time, when n increases, the prior shrinks and will have less of an impact. So if we look at what this means in terms of acquisition function, we have in violet we have the new acquisition function given by PIBO, and in red we have the prior. Here it looks like a Gaussian shape, and then in blue we have the previous acquisition function, right? So the method here clearly is skewing the original acquisition function in blue, because if we had to optimize this acquisition function, we'd probably sample either here or here. But here what we're saying is that this information is important to be considered, and this, as a result, will focus the search towards that part, right? What happens, though, is that over time, when n changes, you see that the prior starts to become flatter and flatter over time. So you start to see that after a bit, you see that, for example, there are other bumps that arise, right? So if we increase n, and slowly the prior is becoming fatter and fatter, flatter and flatter, sorry, and this means that there are other regions that will become more prominent, and they will listen less to the prior over time. Does that make sense? Yeah, good. Right, here you see that the prior becomes really flat over time. Right, so if we illustrate this a little more, we have these high probability regions of the prior that are amplified. So here I'm showing the black box function with this curve, and with x we have the observations. And this is iteration 4. Iteration 6, you see that the focus of the point selection changes, but you also see that after a while you end up sampling things like this, which are very far from your original prior, which is in this region, right? So we went the extra mile, and we were interested in showing that this.
Can I ask one of the practical questions for everyone? I don't want to ask the annoying question how to use a detail. Okay, this is something where users need to default for, because they can't meta tune this. But don't you still have kind of a scaling problem anyhow? Because you're now mixing two things which are on basically two incomparable scales, right? I mean, your acquisition function is basically on the scale of the outcome, and that can be something. And then you're multiplying this with the density. So this is a likelihood value. So I can basically rescale my outcome of the underlying cost function, and then I can arbitrarily get reweighted versions of this, right?
Right.
So I guess this is something that the algorithm should somehow do automatically for me, right?
Absolutely. And so I took like a little shortcut here. For EI, you are subtracting the incumbent, so that problem is not prominent. But for Thomson sampling and GPU-CB, you need to adapt that, and you need to subtract the incumbent from those as well, which is.
If I just do this, this is almost still there, right? Because you're just subtracting an intercept, right? So if my, I don't know, my scale is like, I don't know, kilometers, or I can rescale this to centimeters or something else, and just, I mean, just subtracting the incumbent won't change that, right?
Right, but I think we had rescaled the y in any case, but yeah.
So do you also divide somehow?
I'm not sure I get the question. So I mean, yes, if your objective function is 100 times higher, then EI is 100 times higher everywhere. So what do we care? If we multiply, we don't subtract or anything. We multiply with density.
On log scale, you would add, but which I mean,
well, you ask for scale invariance for, like, you're not invariant to any type of monotonic transformation.
Yes. Yes, but the thing is, I mean, if it's just one objective function, I don't care, right? If I use something that's just the ranking-based algorithm, right? Which all our algorithms are not anyhow. But in this case, we're multiplying two things, and the weighting between these two things matters, right? And I can arbitrarily change that just by going from one unit in my outcome to a different one.
But not from meters to kilometers, which is that, because that's not difficult. But if you take a log, yes.
Well, multiplication is changed.
No, I mean, that EI is just 1,000 times higher, and it's 1,000 times higher everywhere, and you multiply everything by 1,000, it doesn't matter. But taking logs,
Yeah.
Any other questions? Good. So here we show some convergence guarantees. So this the question here was how much worse are we making our optimizer, right, by adding this prior to the optimization? And the answer is that in terms of asymptotic properties, we're not actually adding any overhead. Of course, the evils is when you look at the details under the big O notation here, there is a big constant that in practice may affect you in terms of if you give a weak prior or a very bad prior, it can affect how long it takes to actually find the optimum or one optimum. But this is somewhat interesting that we have this convergence of PIBO in there, so gives us a little bit of peace of mind in terms of what can be done. We've proven this with AI. We didn't prove this with the other acquisition functions. This hopefully will be something that we can do later. So the convergence rate is independent of the choice of prior, which is great. Of course, the dependency is inside the big O notation with this constant factor. All right, so applications to hyperparameter optimization here. So we designed a bunch of different experiments. So we have the synthetic surrogate tasks with Brennan and the Prophet fully connected networks and XGBoost. I think someone was mentioning XGBoost the other day. And we design, we try to design different type of priors to study the properties of this algorithm. So we use strong priors, weak priors, and wrong priors. So strong priors means that they're well located, since these functions are synthetic and we know where the optimum is often, or we have a good estimate of where the optimum is. So we can locate the prior in a good way. Weak means fairly well located, but with a moderate density on the optimal region, and poorly means just take it and put it somewhere else where it's completely different from the optimum, right? And we compare this against random sampling, simply sampling from the prior. One of the questions is what happens if you're just sampling from the prior, right, without doing any Bayesian optimization, for example. This is this baseline here. And Spearmint, which is a common Bayesian optimization framework, initialized with a prior mode. So we take the prior mode and we use that as a default initial configuration for Spearmint, just trying to give the tools that are available, the information, some level of information as well. So this is what we get, the strong priors on the columns, sorry, the priors on the columns and the benchmarks on the rows. You can see that PIBO in blue here and prior sampling in black, and the vanilla BO, the spearmint in purple. You see that compared to the vanilla BO, this approach on the strong prior, for example, gets this nice boost in performance at the beginning, and that's because the strong prior it's leading the optimization at the beginning, and that happens fairly like in most of the benchmarks. What's perhaps more interesting is what happens with the weak prior. So the weak prior is still somewhat helping to speed up the optimization. You can see here and here. And with the wrong prior, you pay that cost by being delayed in the amount of iterations that are needed to somewhat forget the prior and go back to doing normal Bayesian optimization. So the good thing here is that you have theoretical guarantees that this will eventually work, right? So you're not breaking your method, is just being delayed, and the delay can be substantial. Here, for example, you see that you need to run long enough to be able to catch up with spearmint, for example. So the plots here are in log scale, by the way. So if we look at slightly bigger applications, yeah, sorry.
So with the previous slide, do you know how the beta was chosen here? Like
Yes.
What method you used?
Good question.
What was the value?
Yeah, so the question is, how was the beta chosen? So the beta was chosen to be the total budget, here, for example, 100, divided by 10. So that basically gives us somewhat a small percentage of samples that are really affected by the prior, and then the rest gradually fades out.
Thanks.
So it's an hyperparameter. We did some ablation studies as well, and it seems that this simple rule works pretty well across the spectrum. Right. So moving into MLP classification tasks here, we also compare against this method here that was an interesting method that is also doing something similar with this prior injection. However, this method, I didn't talk very much about this, but the way they do this is that they basically they warp the space based on the prior. So you define the prior in a similar way as PIBO, but then what happens is that the search space is warped in an unrecoverable way. So you cannot recover from that warping. So you initially warp the space and then you do search on the warped space, right? This means that if your prior has 0 density somewhere, it's in practice, you're basically chopping the space and not considering that bit of the search space anymore, right? So you cannot recover from that. And we're again using a prior sampling as well, which is interesting to see how it performs compared to the other approaches. So here we see this on the HPO bench. So this six benchmarks. I think that what I forgot to say is that the priors here, since we don't know where the optimum is, which is what will happen in real world applications, what we do is to take the default given by the library and put a prior around the default, right? So a Gaussian distribution centered at the default, and with a sigma that is about taking like 25% of the space.
So you said that other methods, this method can recover that if you have a prior where there's an area where the sink, right?
Will what? Sorry, will shrink.
If you have an area where the prior is 0,
Yes.
you can't recover that. It's basically cutting this out of the search space.
Because it warps, so it warps the space, yeah.
And that's also the case for your method, right?
That's a good point. So we enforce a small density. I didn't say this. We enforce a small density everywhere. So to separate the fact that the space is being pruned with respect to the user just giving a very low density on a part of the space. So we have an additional little density everywhere so that we ensure that the space is not cut off. That's a very good point. Thank you.
Actually, follow up that I haven't thought about, could the same be done for both? Or does the warping then not work anymore? I haven't thought about that.
Yeah.
Before. So for prior sampling, yes, you could do it, but it would also then, be really slow and still not good for misspecified prior. Or GoPro actually does work with the misspecified prior, but for both, I'm not sure. Probably also would be super slow.
Yeah. Yeah, we didn't explore that, unfortunately. Yeah, but that's a good point. Okay, so what we see here, so this experiment is more interesting because we don't know where the optimum is. So the prior can potentially be somewhat wrong, and this is a more common use case where you have a default and you want to have a prior based on that default, right? So what we see here is that Pybo is able to always perform on top of this other curves, and often by a reasonable amount, right? So you can check, for example, the speed up on this, for example. So which is pretty significant. You can see the speed up that you get here, and so on. So in some cases, and you know, we don't know the quality of the prior here. So, but just guessing that the default is a fairly good prior and just giving a distribution across that above that value seems to bring an interesting improvement in the speed up. Another case is on a bigger neural network. So we use this UNet medical segmentation and a smaller version of ImageNet. And we again use the default with these priors on top. What happens for these two applications is that, and we compare against Vanilla BO, there is a very big speed up with respect to Vanilla BO. Here we're talking about 2.5x and even 12.5x here. And in one of these applications, the ImageNet one, there is a leaderboard, and the leaderboard was somewhere around 94%. And this method actually improved a little bit the state of the art of that application by a small amount. All right, so this was for hyperparameter optimization. So this framework is general enough that can be applied also to other applications. And I have a lot of fun, you know, taking these methods that are native of the machine learning community and then applying them to other applications out there. So I'll just show a couple of examples here what that means. So in this application, we are applying this type of methods on the problem called auto-tuning, which is a problem in compiler technology where you are interested in making decisions in the compiler to generate code that goes very fast, for example, or is very energy efficient, or it's small insights for embedded systems and things like that. So there is an objective function of sort, and the compiler tries to generate code through a number of passes, generate code that will go, will optimize that metric. So what we did is to take Pybo, which we implemented in Hypermapper, and use it in a bunch of different real-world programming languages and compilers. So here, Spatial, HPVM, Rise Elevate, for example, and Taco. So these are domain-specific languages, pretty used in some domains. Taco, for example, is a sparse linear algebra language and compiler, very well adopted out there. And the idea is that this programming languages and compilers, they generate code for CPUs, GPUs, FPGAs, and we would like to have one optimizer that is able to just optimize across the board, right? Which is actually a very hard and painful problem in compiler and programming languages today. So can we do that? Can we use one optimizer that optimizes across the board? So I would just show the results for so the answer is yes, we can. Here we'll just show an example for Spatial. A Spatial language specifically is interested in generating code for FPGAs, which is a type of accelerator, which is pretty hard to program, and there are very complex compilers generating code for this exotic computing environment, right? And the idea here is that you want to generate code that optimizes runtime under the constraint that the design has to fit this specific chip, which has a size and cannot be exceeded, right? So it's a constrained optimization problem. The interesting thing, and why I'm talking about Spatial today, is that Spatial has also these Ninja developers that can give you the these priors, and so we use priors in Spatial to see what's the advantage of that. And this is how Spatial looks like. So like all compilers, there are a number of passes. So up here, the user defines a program, which is written in the Spatial language. And then it goes all the way to a number of passes. And eventually, there is the code generation phase where the code is actually generated. And in this specific case, they generate code for this exotic FPGA hardware, right? And the passes, specifically here, there is a pass called Design Space Exploration, DSE, which is a pass that needs to make a number of decisions on how to generate the code. And think decisions that you may take at that make at that point are, for example, if you have a nested loop, you may want to, for example, to break the loop in two. That has a big difference in terms of runtime performance, for example. You can, for example, unroll one loop. So if you have a loop, you can unroll it in a way that you don't only have one instruction, you have multiple instructions, and you change the indices of the loop. So these are all compiler transformations that are commonly used to change the performance of the generated code. And all these decisions need to be made by the compiler. And if the compiler usually compilers use some heuristics. And here what we are doing is to add a machine learning layer at the design space exploration pass, where we have the Bayesian optimization approach, and we also use these priors from the user. So what we get there is that this is the type of performance that we get. So this is an application, which is a shallow CNN, there's a deep CNN, and there's a molecular dynamics application. These are applications that are coded in Spatial, and they go through this compiler toolchain, and eventually we get this type of numbers in terms of performance. So on the y-axis, we have cycles, which is a form of performance. Cycles, meaning how many cycles it takes to run this thing. And this is how many evaluations we need of generated code to optimize the code generation process. One very common approach here, it's OpenTuner, which was developed at MIT. It's a framework that does black box optimization, but using heuristic approaches, like, for example, simulated annealing and things like that. And here we use BoPro, which I didn't present today. It's a previous generation of Pybo. We didn't rerun these experiments on Pybo so far, but BoPro was also from our team, and he has a similar flavor to Pybo, where the priors are injected in the same way. The method is slightly different, but still the same type of method. And what we see here is that the expert configuration sometimes performs pretty badly, sometimes it performs really well, right? And sometimes it's so and so, right? So the same person that does this optimization by hand, and this is given by this flat line, gives us the prior, which is not just one configuration now, it's a little distribution over the space. So the same person injecting this knowledge in two different ways, right? And you see that if you inject it in a way that we can recover and we can improve over that, then the performance that we get is much better than that. For example, there is this big gap here. Here we are able to improve over that, and here we're just basically able to confirm what the user said. Right. Any questions on this? Good. So a second exotic application of prior injection is on robotics. In robotics, we worked in collaboration with a team at Lund University. What they do is to make arm robotic arms to do simple tasks. So here, for example, they're doing peg insertion and obstacle avoidance. So their approach is perhaps not cutting edge in the sense of we can do these things perhaps already with other techniques, but they're trying to have a radically different approach where they have a tree of knowledge with skills, and they try to assemble the skills and put them together. So there are a number of parameters as well that are important to set. Every time you deploy this robot in a different environment, you need to set up these parameters specifically to that environment. These are some of the parameters that they need to set. For example, the arm makes these circles to find the hole, and the path velocity, maximum radius of that circle. Those are parameters that they need to find anytime they deploy this in the real world. And in the obstacle avoidance, they have to avoid the obstacle, and they go into this path, and they want to be safe as well. So they want to have parameters that promote this safety aspect to it. So if we look at a little, I don't have plots for the prior stuff, but it works well. But perhaps instead of showing plots, I will show a little video here of what this looks like. So this is the previous approach, the operator interacting with this Kairos. ROS is it's a framework for robotics, and the operator defines the task, and they have this approach here, which is the skill manager that combines all these different skills. And if you do that, the robot will not be able to really, if you deploy it in a new environment, it will not really be able to do the task. But if they identify these learnable parameters and then they optimize them through Bayesian optimization and injecting also their priors, then the system becomes slightly more complex. But at this point, the robot is able to learn things in simulation and eventually get to the point where these parameters are learned, and for every new environment, they just have to push a button, learn this in simulation, and then it works also in the real world. So the reality gap for this application setting is not very wide. So that can be done in simulation, and this is the real world experiment. So again, it's a fairly simplistic approach. It's more of a proof of concept. Then robots can do things that are more complex than this today. But this new approach, driven by learnable parameters through Bayesian optimization, leads to have a fairly generalizable with respect to the environment that they deploy the robot in. Any questions on this? It's a little fun application of this work. So if you are a user and you just want to use Bayesian optimization with priors, what do you do, right? So I don't really care about all these acquisition functions, all these things. I just want to use this, right? So the PyBo algorithm is implemented in 3 different frameworks, and the fact that it's pretty easy to implement was good, because we've been able to implement it in a bunch of different, actually even more. I think that Frank and Marius, maybe they're using it also in other frameworks as well. But it's implemented in Hypermapper, which is a framework that we maintain in my team. SMAC supports PyBo as well, so just go check it out. And we have an implementation in Spearmint as well. It's not available because the code is a little messy, but we can potentially give it to you if you're interested. And this is how it looks like. So after this lecture, I think you should be able to go to this page here, and now you will probably understand what we're talking about by reading the keywords, and you will just be able to download the framework and use it. At least this is my hope after this lecture. Right, so conclusion. So we have presented a human-centric approach to hyperparameter optimization. PyBo is flexible across many acquisition functions. I'm using myopic here. It's a specific term. Acquisition functions like Thomson sampling, GPUCB, EI, and what's called probability of improvement. It doesn't work out of the box with the information theoretical approaches. That's why I didn't really talk about them right here. But we are trying to extend that framework for those approaches as well. It's effective and conceptually simple, which is a strength, I think, and it really helps in low budget applications. Like, for example, if you have to do hyperparameter optimization of neural networks, you only can train perhaps, I don't know, maybe a few tens of architectures in total, right? If you're generous, right? There is no expertise in BO nor machine learning needed to use this stuff, right? So that's also pretty convenient. And injecting the user prior beliefs is very, very simple. You don't need to know about the kernels. You don't need to know about difficult machine learning concepts to use this, right? So in future work, we receive this question fairly often. So what if I can, to train my neural network, I can only use 10 samples. I cannot do more than that, 10 trainings. What can you do? And probably PyBo will not be very, very effective because 10, it's really a small number, right? So we're working now on this topic, and Niratoi here has been pushing a paper at the meta learning workshop at NeurIPS. It's not available yet, but if you're curious to know what's the type of approaches that we're using there, let me know. We can share the manuscript. And of course, using multi-fidelity is what's going to help, right? So if you have information, if you have a gray box optimization problem instead of like a black box, then you want to use the additional information that comes from potentially being able to look inside the box. And a few other talks in this event talked about multi-fidelity before. We would like to be able to integrate beliefs over optimal values, not just the X, but also the Y. Sometimes we know what the values on the Y-axis, for example, accuracy, you probably know that it's something 90-something or something. You will know that, and you will be able to potentially inject prior knowledge with respect to that as well. We are interested in looking for a slightly more principled Bayesian approach to this, and we are doing some work on that as well. Right now, it's not fully Bayesian. The update is not fully Bayesian, which is a little intellectually slightly unsatisfying. And we will extend PyBo to non-myopic acquisition functions, specifically to entropy search methods or information theoretical methods. If you're interested in digging more this topic, there are a few resources from our team. These are the 4 papers we worked on in the last few years. And so have a look and ask me if you have questions. There is other literature on priors, and there is more literature over time. I think that this human-centric hyperparameter optimization is becoming a little bit more known now, and there are more methods appearing. If I had to recommend 2, I would probably recommend this one to read, and perhaps this recent method. There's a pretty interesting approach as well. And if you're interested in going back and understanding a little more of Bayesian optimization, if you're just a user, you don't really need to understand much more than this. But if you are working on this topic, perhaps you can, and starting to work on this topic, you can read these 2 reviews that are pretty well done. Further topics in BO. So BO is an open research problem. So applications work for, as I was saying, 10, 20 variables, but there is much more that we can do. We can scale this up to perhaps hundreds of thousands of variables. There is large scale BO where you have a budget that is fairly large, thousands of observations, for example. There are non-myopic approaches, which are information theoretical approaches, which are, I think, very including information theoretical approaches that are very interesting because they have a slightly different way of seeing things, and in my opinion is the good way, even if the performance doesn't show that so far. Perhaps you will do in the future. And multi-objective, very important topic as well, and parallelization through batch Bayesian optimization as well. This is all I have for my talk today, and I think we have 5 more minutes for questions.
Is there work on learning these priors?
That's it. So in the robotics paper, we actually tried that. So what happens if we just use some prior experiments and we create with a KDE we create those priors from priors. So basically a meta learning approach, and it works. It works actually pretty well. But just one experiment, so I will not be able to say in general. Of course, there are many other meta-learning techniques that can be used. So this work focuses a little bit more on the human-centric approach, while there are other techniques that I didn't really talk about here in this talk that do that perhaps even better, right? We don't know in that sense.
Great talk, thank you. Regarding the compile optimizations, are there still any open challenges you are currently working on, or is everything working fine so far?
Right. So I think so we use Bayesian optimization in those type of applications since probably 2015, so a long time ago. But I think that we were being a little bit naive in the way we were implementing it. I think that compilers as a domain has specific things that need to be taken care of. An example is permutation variables. So if you have 6 nested loops, a compiler transformation is to just shuffle them around. So that's a permutation variable. And permutation variables are not super common in Bayesian optimization, for example. It's very important to be able to deal with categorical and discrete variables for this type of problems, because there are no continuous variables, and the machine learning community has been focusing on Bayesian optimization on continuous variables mostly. Then of course there are extensions. So we have a paper that will be published on arXiv in about 2 weeks that talks about these open challenges for Bayesian optimization in the context of compilers. And I can share the paper, the arXiv version with you. Is being submitted in 10 days. So those are a couple of things. One more thing perhaps is the way you set the length. So it becomes a little technical, but the length scales for the length scales for the GP, you can improve the way if you set gamma priors on those length scales, you get better performance on compiler applications. But this becomes really technical. What we are trying to do with that project is to try to provide a design space exploration tool that can be just used by compiler experts without digging into this type of details.
In the existing implementations of FIBO, in what form can the user specify the prior distribution?
Right. So excellent question. So this is this, I think, slide here. Oh no, sorry. All right. So this is the main 3 methods you can use. So if you have a named distribution, for example, you can use something like this. If you have many of those are accepted in input. Discrete variables, you define your list of probabilities. And if you have density estimation as well, if you have a bunch of observations that you want to give in input, then it will calculate a KD, and then it will give you this. You can inject both univariate distributions, but also multivariate distributions. But it turns out that users are more familiar with the univariate. It's easier to inject, right? It's easier to draw, and so they usually use univariate. But it doesn't seem to be hurting the optimization algorithm very much. Of course, if you have multivariate, perhaps it's better.
Saying that people don't use BO as much like you use because they cannot inject the prior knowledge. But now you're essentially asking the user to be able to specify the prior knowledge in terms of probability distribution, which is, I think, quite a burden on the user to be able to express even if you have options. In my experience, people using Bayesian optimization techniques, they often have like a general idea of how variables interact with each other. Like if you put a point here, make sure there's also, I don't know, but they may not necessarily be able to express that in terms of probability distribution. So there's some layer that could somehow make that interface really make this even more accessible.
Right. So I think if we had a little more funding on this project, I will just give a tablet in interface and maybe drawing, but that would be only in two-dimensional. So that's a good point. So finding a way to inject the prior in a slightly more flexible way. So you're basically saying we would like to be able to capture the dependency between variables and
I mean, we have applications, for example, structural mechanics, we know that here.
right. In some
Essentially, it's like I could express it perhaps as constraints, and then you may want to decrease the relevance of the constraints, of forcing me to express it in terms of continuity.
So right now you can already define something as multivariate by if you think, for example, there is a Gaussian shape around the region, even if it's multidimensional, you can already do that. But if it's a more complex form, then perhaps you can do something like this, but it's not ideal. That's not ideal. In terms of constraints, of course, there is the Bayesian optimization with constraints, which I didn't talk very much about, but that's a different topic. Yeah, so I will go there. That's an interesting, yeah, so you can have multiple experts, that's true. I didn't think about that. So you can, at the end of the day, you want to find, you want to merge these two distributions together somehow, right? So that's, I think, doable in that sense, right? So one of the things you can do in the specification of this problem, you can define also multiple Gaussians. So you define multiple peaks of the Gaussians, and then it computes like a, what do you call it? Gaussian mixture model. So that's a way. So if you have a Gaussian from one expert and another Gaussian from expert, the interface will allow you to actually input that, and it will automatically merge them together, basically. So we didn't think about the multi-user type of thing, but we really thought about the fact that you may have multiple Gaussians, and the user will inject those multiple Gaussians, for example, and then you have to find a combination of those. Yeah.
I was saying, you can also try to I don't think it should make sense to do that. Very useful, because you may actually have two regions here, maybe sometimes I don't know about those, if you need to do
No. It's a mixture of Gaussians. So you will still preserve these modes, and you will get a little bit of volume as well in the middle. Yeah.
I have a related question. This is actually this group decision-making systems. So the idea is, because we talked also for compiler optimization and all things, and I saw that you also work with database optimization, so that's what I'm interested in mainly. And the idea is that how do you actually define the space of user trials? So, for example, how could I design this domain-specific language for optimization of my own application? What is too much user prior? Is this weakness over the system? Is there too little user prior, for example? I want to be in the list of probability here, or there's some distribution, things like that. So how do I design this for?
How do I design? So
I have an X application, for example, for databases.
Yeah.
How do I think what are my user priors? So
right.
How can I actually extract the ninja knowledge? Right.
So databases is it's an interesting problem. I didn't talk about this at all, but we do work on optimizing databases automatically as well, and using techniques like this. And so in practice, I was mentioning before that you have a default usually in a library. So you would, if you don't have any other information, you would use that default, and you just create a prior distribution around that default, right? And that usually works pretty well, as the experiments show. In databases, there are these defaults, which are in some database management systems are actually really, really bad, because they are assumed to work on your small device and then the big data center. So usually they are not very good in that sense. So we define priors using expertise, database administrators that know how to define those priors, meaning that if you're running on a data center, you're probably looking at this region here. If you're doing on a small device, you probably look at something different. So that type of, so always an expert in the process that gives you that type of information, or the defaults from the library, one or the other.
And one quick question that I think we should ask pretty much in every BO talk about benchmarks. So we have these results on BoPro, and as you said, we haven't rerun Hybo because it's annoying. We don't know how to run this black box function anymore because it ran sometime. Can we encapsulate it in a container, plug it into HPO bench? Can we do that with your robot tasks and so on? I think that would be really helpful if everybody sort of thought about that at the time that they're doing the experiments, not 6 months after when they're asked to actually get those.
So for the compiler stuff, it's actually not as trivial because those are real-world applications that are a little bit difficult to install, and they have dependencies and so on. So
and that's the whole point of HPO bench, right? You containerize it once,
right,
and then it's containerized.
Right.
Would that be possible, or
maybe definitely on so I think it's possible if we use that approach. Yeah, I think it's potentially possible, and that would be very valuable. I think I agree with you. I think there was a question over here.
The very last one then.
Is a question over here? You're good. Okay.
So then, thank you again for the speaker. Thank you for having us.